Okay, so we're going to talk about sequences, and in particular, the focus of this section will be on infinite sequence. All right, so as discussed in earlier videos, we talked about sequences, how they're represented, whether via just a list of ordered numbers, some kind of formula, explicit formula, or a recursive formula. Right? Now, our notation here in this section, since we're dealing with infinite sequences, we'll assume that our starting point will always be 1, right? Some textbooks make a use 0 as a starting point, but here for our reference, whenever we see the notation here with the curly braces here in a sub n, we'll assume we're referring to a sequence where the first subscript is 1 going to infinity. Right? And kind of list it out. We have a1, a2, etc. here, just kind of infinitely, right? No endpoint here. All right, and some cases we can think of the sequence as some function that's defined only at the positive integers, 1, 2, 3, etc. Right, so it's a kind of a discrete function, which is not what we're used to kind of working with when we're in algebra. We think of a continuous function, right? So for example, let's say that my a sub n is 2, 1/2, or let's just use this here. 1/2 to the n minus 1. Right, and we can think of plotting the points here. Right, if you think of a1 is 1, right? a2, plugging it in, is 1/2, a3, 1/4, and a4 is 1/8. Right, and we can think of the subscripts kind of as our domain, right? But it's only defined on the integers, right? Positive integers, 1, 2, 3, 4, right? So we can think of this, and then a half, right? A fourth, and then an eighth, right? So it's just defined on those 4 numbers, right? And notice it's different than what we've done before, where we think of it as x as just being the real numbers here, right? So there are correlations with our algebraic functions like f of x, and we can use similar techniques in working with sequences. And we'll see one of them, for example, is let's say that we are interested in finding the limit of a sequence. All right, so our first example, let's say that our sequence was defined as n over root of 10 plus n. All right, so the first step is I'll set up my limit, the limit as n goes to infinity, and I'll look at the explicit formula, root of n plus 10. I'll rewrite it like this. All right, and again, just recalling some techniques of evaluating limits at infinity when we're working with the limits. For something like this, an algebraic function, what we're going to do is we're going to focus on those leading terms, right? Because we're thinking of really, really large values of n. So when I'm adding a constant here, that plus 10, right, won't contribute much to the limit, right? The leading, the driving forces here behind evaluating this limit are going to be what's changing, right? 10 is always 10, right? But n is going out towards infinity, right? A million, a trillion, right? Like incredibly large numbers for n, right? So these are going to dominate here in trying to determine what our limit is. So when we do that, we can think of this here. Right, and then simplifying, you can think of the limit as n goes to infinity, n to the 1/2. Right, just kind of subtracting the exponents, and we can see here that this goes to infinity. Right, so I've now found the limit of this particular sequence. Now let's do one more example, right? So for our second example, how about we want to take the limit ln of n over n. So I start off again by setting up my limit as n goes to infinity of L of n over n. Right, now looking at this is much different than the previous one, right? It's not an algebraic type function. The ln of n is one of our transcendental functions, right? They don't follow the conventional rules of algebra. So what we can do here is we can use techniques that we learned previously in this class when we look at the limit here, and we know that ln of n and n, both of those are going towards infinity. Right, and so we can think of the sequence as a function defined across the intervals, and we can apply the same techniques that we do for functions that involve x. Right, and in this case, I will use L'Hopital's rule. And so that tells me here I'm in the indeterminate form. So I'm going to take the derivative of each individual part, right? The numerator, so that's 1 over n, and the denominator is 1, and then just simplifies to this. All right, and now I can evaluate this limit as n goes to infinity. It grows really large in the denominator, and 1 over a really large number is a small, very small number. In fact, it is converging to 0. Okay, so now we have here two different sequences here with very different types of behavior. Right? One of them, the limit of the sequence is going to infinity. The other one, the limit is going to 0. So now we have a name that we're going to designate to these both of these types of sequence, and that is what we're going to call convergence. So let's define that here. So the limit as n goes to infinity of a sub n is equal to L. Right, now if this value of L is less than infinity, right, in other words, is some constant, right, then we say that the sequence a sub n is convergent. Right, if L goes to infinity as n is going to infinity, then a sub n is a divergent sequence. All right, so for our above examples here that we did, right, for the first one, right, when we have it's equal to infinity, then this is a divergent sequence. When we get a finite value, right, we say that this is convergent. Okay, now as we have seen here, we use techniques that we use with functions here, and we can define here this idea that, for example, the limit of L of n over n, we think of the sequence being some function defined across just our integers, right? So we can think of f of x, the corresponding algebraic function, or the corresponding function would be f of x equals to ln of x, right? And then that implies here that the limit as x goes to infinity of f of x is equal to L. Well, that would mean that the limit as n goes to infinity of f of n is also going to be L. All right, so that means that, right, if they follow the same behavior of the functions, then we are able to use the different limits that we have learned, different limit laws that we learned before. Right, so for example here, if we so here's from our textbook, section 5.1, the algebraic limit laws. So as n goes to infinity of a constant, right, there's nothing to plug in, it's the constant c, right? And then we can factor out a constant c. We can split up the limits of the sequences across sums and differences, and across products and quotients as well, right? We can treat them individually, right? As long as, of course, the b for the quotient is not 0, right? And b sub n is not 0 for any value of b sub n. Okay, and we can use techniques like L'Hopital's rule, right, when it is appropriate.